A neutrino is a fermion that interacts only via the weak subatomic force in gravity. The mass of the neutrino is much smaller than that of the other known elementary particles, although only differences of squares of the three mass values are known as of 2016. Cosmological observations implied that the sum of the three masses must be less than 1/millionth that of the electron. The neutrino is so named because it is electrically neutral and because its rest mass is so small that it was long thought to be zero. The weak force has a very short range. Gravity is extremely weak on the subatomic scale, and neutrinos, as leptons, do not participate in the strong interaction. Thus, neutrinos typically pass through normal matter unimpeded, and undetected weak interactions create neutrinos in one of three leptonic flavors: electron neutrinos, muon neutrinos, or tau neutrinos, in association with the corresponding charged lepton. Although neutrinos were long believed to be massless, it is now known that there are three discrete neutrino masses with different tiny values, but they do not correspond uniquely to the three flavors. A neutrino created with a specific flavor is an associated specific quantum superposition of all three mass states. As a result, neutrinos oscillate between different flavors in flight. For example, an electron neutrino produced in a beta decay reaction may interact in a distant detector as a muon or tau neutrino for each neutrino. There also exists a corresponding antiparticle, called an antineutrino, which also has half-integer spin and no electric charge. They are distinguished from the neutrinos by having opposite signs of lepton number and chirality. To conserve total lepton number, in nuclear beta decay, electron neutrinos appear together with only positrons or electron antineutrinos, and electron antineutrinos with electrons or electron neutrinos. Neutrinos are created by various radioactive decays, including in beta decay of atomic nuclei or hadrons. Nuclear reactions such as those that take place in the core of a star or artificially in nuclear reactors, nuclear bombs or particle accelerators. During a supernova, in the spin down of a neutron star, or when accelerated particle beams or cosmic rays strike atoms, the majority of neutrinos in the vicinity of the Earth are from nuclear reactions in the Sun. In the vicinity of the Earth, about 65 billion solar neutrinos per second pass through every square centimeter perpendicular to the direction of the Sun. For study, neutrinos can be created artificially with nuclear reactors and particle accelerators. There is intense research activity involving neutrinos, with goals that include the determination of the three neutrino mass values, the measurement of the degree of CP violation in the leptonic sector, and searches for evidence of physics beyond the standard model of particle physics, such as neutrinoless double beta decay, which would be evidence for violation of lepton number conservation. Neutrinos can also be used for tomography of the interior of the Earth.